I want you to picture something for a moment. You are standing on this meticulously clean factory floor.
Right, the kind with the really bright lights.
Yeah, exactly. It's bright. The walkways are clearly marked with that thick yellow safety tape, right?
Yeah, perfectly organized.
Perfectly organized. And right in front of you is a perfectly functional, incredibly expensive piece of industrial equipment.
We're talking state-of-the-art stuff here. Millions of dollars of capital investment just sitting right in front of you.
Literally millions. And the machine's green status light is glowing brightly.
Meaning it's healthy.
Exactly. The operator is standing right there by the control panel. You know, they're fully trained, fully paid, and they are completely ready to go. But absolutely nothing is happening.
Which is just the worst feeling.
It is. There is zero humming, zero cutting, zero output. And right directly in front of the machine, painted perfectly on the ground, is an empty floor square labeled Next T Job.
Yeah, it's totally empty.
Right. So the machine is healthy, the person is ready, and yet the company is just bleeding money by the second.
It's a painful image. I mean, really painful. And the crazy thing is, it happens thousands of times a day in almost every facility on Earth.
Thousands of times.
Yeah, you have this massive asset that is, technically available, but it is effectively starving.
And that image, that starving machine, is the mission of today's deep dive. We are going to unpack one of the most ordinary yet staggeringly expensive misunderstandings in modern industry.
It's completely hidden in plain sight.
It really is. It's this hidden bottleneck where machinery is perfectly healthy, completely ready to go, but the work simply isn't ready. And, well, the cost of this illusion is mind-bending.
Oh, the financial impact is huge.
Yeah, I was looking at some data from Pingdom that we pulled for this deep dive, and get this, 98% of organizations estimate that a single hour of downtime exceeds $100,000 in costs.
Yeah. $100,000 an hour is just the baseline for many of these operations.
A baseline? That's insane.
I know, but think about it. When you have a complex supply chain relying on a specific component, a machine not cutting metal or, not molding plastic, it isn't just a localized delay.
Right, it ripples out.
Exactly. It cascades. It delays the assembly line, which then delays the shipping department, which incurs penalties from the end customer because you're late.
Oh, right, late delivery fees.
Yeah. So when we talk about a machine sitting idle because the next job isn't physically in that yellow square, we are talking about a catastrophic financial leak.
A leak that somehow nobody seems to be panicking about. I mean, if a machine breaks down, people run around with their hair on fire, right?
Oh yeah, alarms going off everywhere.
Right, alarms, maintenance crews sprinting across the floor. But if the machine is just sitting there, waiting, people casually walk right past it.
They don't even notice.
Right, and I want to understand how companies are letting this happen right under their noses. So, looking through the stack of materials we have today, we've got some really fascinating industry reports from UL Solutions and Advanced Technology Services.
ATS, yeah, they do great work on this.
Yeah, plus some deep operational analyses from groups like ManuApp and Azure Digital. And a common thread I noticed across all these sources, and this is wild, is that the very language we use to describe a stopped machine is actually lying to us.
Yeah, the vocabulary of manufacturing is, well, it's designed to protect people, not to expose truth.
Protect them from what? Management.
Basically, yeah.
Yeah.
We are dealing with a fundamental misunderstanding between a machine failing and an organization failing to feed the machine.
Okay, break that down for me.
So we have to separate the concepts of availability and readiness. In industrial terms, a machine is considered available if it can physically run.
Like it turns on.
Exactly. It has power, it isn't broken, it's mechanically sound, the safety guards are in place. But a job is ready only when every single condition required to start it is confirmed and physically present.
And those conditions, I mean, from what I read, it's not just having a block of steel to cut. The stack of requirements is massive.
Oh, it's a huge checklist.
Right, like you need the exact correct material, the correct quantity of that material, the specific tooling fixture to just, hold it in place.
Yeah, and the data too.
Right, you need the current revised engineering drawing so you aren't cutting apart to some obsolete specification.
Which happens all the time, by the way.
I bet. And you need the right inspection gauges calibrated and at the station. And you need the formal signed approval from quality control or engineering to actually begin the setup.
Yeah.
So if even one of those elements is missing, the job isn't ready. The machine is available, sure, but the organization's productive capacity in that exact moment is absolute zero.
Which brings us right back to the language issue.
Hmm.
When a machine is sitting there, totally healthy, but waiting on, say, a quality control signature, how does the operator log that time?
Right. What do they write down?
Well, they don't have a button on their console that says organizational failure.
That would be amazing if they did, though.
Right. But they don't. So they log it into the system using euphemisms.
The euphemisms in these reports are incredibly frustrating to read. I mean, they log it as an operational delay or like a minor stoppage.
Just waiting.
Just waiting. But the one that really gets me, the one that makes me laugh, is coordination issue.
Well, coordination issue is a masterpiece of corporate doublespeak.
It really is.
I mean, it softens the blow perfectly.
Hmm.
It removes all accountability. And because nothing failed dramatically enough to demand immediate attention, because there's no smoke, right? No
Yeah.
sparks, no loud grinding noise.
Right, nobody's bleeding.
Exactly. This form of downtime is incredibly quiet. When a drive motor blows up, alarms go off, the maintenance team rushes over, and there is this massive root cause investigation.
Clipboards everywhere.
Exactly. But when a healthy machine is just waiting on a forklift driver who, maybe is on a coffee break, there's no drama. It's quiet. And because it is quiet, it just becomes background noise. Management ignores it.
Okay, I have to challenge this a bit, though. Let's play devil's advocate.
Sure, go ahead.
If a machine is waiting, say, 15 minutes for a forklift to bring a pallet of material, isn't that just a minor scheduling hiccup? I mean, reality is messy.
True. Reality's very messy.
Right, people get delayed. Traffic in the warehouse aisles happens. Why are these operational analyses treating a 15-minute wait like a critical systemic failure that requires a massive intervention? It feels like we are, I don't know, overreacting to normal daily friction.
I hear that a lot. And if it only happened once a month, yeah, it would just be a minor hiccup.
Right.
But we have to look at the mathematics of compounding delays. Let's trace a single, perfectly healthy machine through just a standard Tuesday.
Okay, a standard Tuesday. Let's do it.
At 8 a.m., it waits 20 minutes for material to be brought from the warehouse.
Okay, 20 minutes. Not terrible.
Right. Then at 11:30 a.m., it waits 10 minutes because the operator can't find the specific drill bit required for the next operation.
Okay, up to 30 minutes.
Then, at 2:15 p.m., it waits 15 minutes because the operator is trying to get a clarification on an engineering drawing that has a typo in it.
Okay.
That is 45 minutes of lost production in a single shift.
45 minutes out of an 8-hour shift.
Right. Now multiply that by 2 shifts a day.
Okay, so that's an hour and a half.
Multiply that by 5 days a week.
Wow. Okay, we are at 7.5 hours.
Exactly. You are losing an entire shift of production every single week, not because the machine is broken, but because of these so-called minor hiccups.
An entire shift just vanishes.
Just evaporates. Over the course of a year, that machine is losing productive capacity just as surely as if the main drive motor blew out and the machine was physically broken and red tagged for 6 solid weeks.
6 weeks.
Yeah. But because it happens in 10-minute increments, nobody launches an investigation. Nobody panics.
It's literally death by 1,000 paper cuts.
Exactly that.
And the financial impact of that, going back to the $100,000 an hour thing, is staggering. But honestly, this concept of availability versus readiness, it extends way beyond a factory floor.
Oh, absolutely. It's everywhere.
Like, if you manage any kind of team, this exact same invisible waste is happening. Think about a hospital emergency room.
That's a great example.
Right. An operating theater might be clean, sterilized, and perfectly available. The surgeon is standing there, scrubbed in. But if the anesthesiologist is delayed or, I don't know, the patient's updated charts haven't been pushed to the IT system, the surgery isn't ready.
The room is available, but the hospital's capacity is 0.
Right. The surgeon is just standing there.
Software development is another perfect parallel.
Oh, tell me about it.
You have a highly paid senior software engineer sitting at their desk. They have their dual monitors, their fancy coffee, their development environment is booted up. They are available.
They're ready to code.
But if they're waiting on a product manager to finalize the requirements document for the feature they're supposed to build, the work isn't ready.
So what do?
They end up scrolling through forums or doing low-value administrative tasks. The resource is available, but the workflow is starved.
It's crazy. We focus so entirely on the asset, like the machine, the surgeon, the software engineer, and we completely ignore the invisible workflow that actually feeds that asset.
Exactly. And to expose that invisible workflow, We have to stop relying on these vague categories like coordination issue.
We have to ditch the euphemisms.
We have to look at the hard metrics of performance. We have
Hmm.
to strip away the emotion and just look at the math.
The brutal math.
Right. The reports from ATS and Makula dive deep into this, but they use a lot of industry jargon. We need to decode the alphabet soup of reliability, availability, and utilization.
Yeah, I was reading through the Makula report, and I have to admit my eyes start to glaze over a bit when I hit those terms.
It happens to everyone.
They differentiate heavily between reliability and availability. But intuitively, if a piece of equipment is highly reliable, doesn't that inherently mean it is available?
You would think so.
Right. What is the actual functional difference between those two words on a factory floor?
It is a really common point of confusion, but the distinction is critical for troubleshooting. Let's start with reliability.
Okay, reliability.
In technical terms, ATS defines reliability as being measured by mean time between failure, or MTBF.
Mean time between failure.
Okay.
Simply put, it's the statistical probability that a machine will run without breaking down while performing its intended function. It's a measure of engineering robustness.
So how tough the machine is.
Right. If a machine runs for 500 hours and breaks down 10 times, your MTBF is 50 hours. The higher the MTBF, the more reliable the machine. It tells you about the quality of the machine's running time.
Got it. Okay, so reliability is entirely about the physical health of the hardware. Like, will it snap a belt? Will the motor overheat? Will the hydraulics leak?
Exactly. It's about the iron. Availability, on the other hand, is a ratio of time. It is the actual operating time divided by the planned production time.
Okay, give me an example of that. Sure. If you schedule a machine to run for a 10-hour shift, which is 600 minutes, but it only actively operates for 500 minutes because it was jammed, or being repaired, or waiting for a setup, your availability is about 83%.
Okay, I see. So the machine can be perfectly reliable. Like, it literally never breaks down. The MTBF is basically infinite. But it could still have terrible availability if you spend, say, 3 hours every shift just setting it up for the next job.
Precisely.
The machine isn't failing. The process of managing the machine is failing.
Exactly that. Reliability is about the quality of the runtime. Availability is about the quantity of the runtime.
Quality versus quantity. Got it.
But here's the kicker. Neither of those actually tells you if the business is making money.
Wait, really?
Nope. For that, we hit the third metric, utilization. And according to the Makula data, this is where the truth absolutely hurts.
Right, because utilization measures how much time a machine is actively running compared to the total time it could theoretically run.
Right, exactly.
And Makula reports that many factories operate with a machine utilization rate of somewhere between 25% and 60%.
Yeah, just let that sink in for a second. 25%.
That's horrifying.
You mean 75% of the time a multi-million-dollar capital asset is sitting there doing absolutely nothing?
It's wild. But you know, Makula also makes a claim that completely breaks my brain.
Oh, about the 100% target.
Yes. They say the target for utilization should not be 100%. They argue that a world-class target for utilization is actually around 80%.
Yep.
Why on earth would a business spend $2 million on a machine and then intentionally plan to leave 20% of its capacity on the table? I mean, if I buy a machine, I want it running every single second of every single day to pay for itself.
It feels completely counterintuitive, I know. But pushing for 100% utilization actually destroys complex systems.
How so?
It comes down to the physics of queuing theory and variability.
Queuing theory.
Okay. Yeah. If you schedule a machine for 100% of its available hours, you leave absolutely zero buffer. You leave no room for planned pauses, no time for complex tooling changeovers, no time for deep cleaning, and critically, no time for preventative maintenance.
So you are basically just running it until it explodes.
You are running it until the entire schedule explodes. Think about a highway.
Okay, a freeway.
If a highway is a 100% utilization, meaning every single square foot of pavement has a car on it, what is the actual speed of traffic?
Oh, it's zero. It's a parking lot.
Exactly. It's a parking lot. At 100% utilization, any tiny variation like one driver tapping their brakes causes a massive shock wave that ripples backward and stops the entire system.
Oh, wow, yeah. The phantom traffic jams.
Right. Factories work the exact same way. If you schedule a machine for 100% of its time, the moment one single thing goes wrong, a material delay of like 5 minutes, the entire week's schedule cascades into failure because there is no slack to absorb the delay.
You need the empty space to move.
Yes. Targeting 80% gives you strong output while acknowledging that reality is messy and friction actually exists.
That highway analogy makes perfect sense. If you have no space between the cars, movement is impossible. But looking at these three metrics, Reliability, availability, and utilization and isolation feels, I don't know, flawed.
Oh, it is. Very flawed.
Like, if I utilize my car to drive in circles in an empty parking lot, it is 100% utilized, it's highly available, and it's reliable. But it is 0% productive. I haven't gone anywhere.
Right, you just wasted gas.
There has to be a metric that captures the actual value of that running time.
Which brings us to the core of the analyses from Azure Digital and UL Solutions. They point to one metric to rule them all.
The big one.
The big one. A metric that takes all these fragmented pieces of data, smashes them together, and produces a single, unforgiving percentage. We have to look at overall equipment effectiveness, or OEE.
OEE. I've heard this tossed around as the gold standard, but the math behind it is where the illusion of a good job really shatters.
It's ruthless math.
It really is. The formula is OEE equals availability multiplied by performance multiplied by quality.
The multiplier effect is what shocks people. We are so used to averaging things. But inefficiencies in a system do not average out. They compound.
Let's walk through a tangible example of this math because it's brutal. Let's imagine a specific machine on the floor.
Okay.
We measure its availability and it comes in at 80%.
Which means it's running 80% of the time it was scheduled to. Not bad.
Right, not bad at all. Then we measure its performance. This means when it is running, how close is it to its maximum theoretical speed? Let's say it's running at 90% of its max speed.
Pretty good.
Pretty good. Finally, we look at quality. Out of all the parts it made, how many were actually good? Let's say 95% of the parts are perfect and 5% go in the scrap bin.
Standard defect rate for some places, sure.
Right. So if I bring those scores home on a test, an 80, a 90, and a 95, I am thrilled. I am a solid B plus A minus student. My parents are taking me out for ice cream.
But OEE doesn't care about your feelings. And it definitely doesn't average the scores. It multiplies them.
Okay, let's do the math.
You multiply 0.80 by 0.90 by 0.95. The result. Your OEE is 68.4%.
Oh, man. You went from an A minus student to a D plus. You are barely passing.
Really? Because every time you introduce a inefficiency, it amplifies the previous one.
Right. They stack.
Yeah. You were only available 80% of the time, and during that limited time, you were running slow, and of the parts you made while running slow, 5% were garbage.
The compound effect is devastating.
It really is. Azure Digital notes that a world-class OEE is considered 85%.
Yeah.
But the average factory, the factory that thinks it's doing a pretty good job, is sitting somewhere in the 40% to 60% range.
Wait, a 40% OEE. That means 60% of your theoretical manufacturing capacity is just vanishing into thin air? Where is it actually going? Like, what are the specific mechanisms dragging these numbers down?
Well, the Total Productive Maintenance Methodology, or TPM, categorizes this leakage into what they call the 6 big losses.
The 6 big losses.
Yeah, we need to unpack these because they explain the why behind that terrible math.
Okay, let's go through them.
Let's look at the first factor, availability. The two losses here are breakdowns and setups.
Okay, breakdowns are obvious. The machine snapped a belt.
Right. But setups and adjustments are more insidious. This is the time it takes to switch from making part A to making part B.
The changeover time.
Yeah.
Wow.
If your setup takes 3 hours because the operator has to walk across the massive factory floor 10 times to find the right wrenches, your availability plummets.
Okay, so availability is lost to breaking down or setting up. What about performance?
Performance is dragged down by minor stoppages and reduced speed. We talked about minor stoppages earlier. The 30-second delays where, say, a sensor gets covered in dust, the machine halts, the operator wipes the sensor, and hits start.
Right, it's so fast it barely registers.
Exactly. It's so fast it doesn't get recorded as a breakdown, but if it happens 50 times a day, your performance metric is destroyed.
What about reduced speed? That sounds intentional.
It often is, and it's even quieter. Sometimes an operator will intentionally turn the dial down and run the machine at 70% speed.
Why would they do that?
Well, maybe the material they received is slightly harder than usual, or maybe the cutting tool's getting dull and they just don't want to bother changing it yet. The machine is running, it looks busy, but it is silently bleeding capacity.
So they are padding the process to avoid a breakdown, but in doing so, they are tanking the performance score.
Exactly. And finally, we have quality. The two losses here are startup rejects and production rejects.
Startup rejects.
Yeah, that happens when you first turn the machine on for a new job. You have to make a few parts, measure them, adjust the dials, make a few more. You're literally planning to make garbage until the machine is dialed in.
Oh, I see. It's just part of the warm-up.
Right. And then production rejects are the defects that happen during normal running of tool chips or the temperature fluctuates. And you make a bad part that has to be thrown away.
So you have these 6 big losses constantly attacking the machine's efficiency. But I want to look at this from the perspective of the human being standing in front of the control panel.
The operator.
Right. If I'm an operator and my manager comes down to the floor, points at a dashboard, and yells at me because my machine's OEE is 45%, how do I defend myself? Is it my fault? Is it the maintenance department's fault? Is it the warehouse's fault?
It's a great question.
It just feels like OEE could easily be weaponized by management to just blame the frontline workers for everything.
That is a very real danger, and it's why UL Solutions provides a critical distinction in their reporting. The difference between net OEE and gross OEE.
Net versus gross.
Yeah, if management doesn't understand this difference, they will absolutely weaponize the data incorrectly.
Break that down for me. What is the difference?
Let's create a scenario. Imagine a CEO sitting in a high-rise office in New York, looking at a dashboard for a manufacturing plant in Ohio.
Okay, classic corporate setup.
The CEO sees a gross OEE of 30%. They pick up the phone, furious, and threaten to fire the plant manager because the factory is clearly failing.
Right, 30% is terrible.
But the plant manager in Ohio pulls up their own data and says, my net OEE is 95%. My team is operating flawlessly.
Wait, how can they both be looking at the exact same machine and see a 65-point difference in performance?
Because they're measuring against two different types of time. Net OEE measures the machine's performance strictly against its planned scheduled time.
Okay, planned time.
Right. If the plant manager only schedules the machine to run for one single 8-hour shift per day, net OEE tells you how well the operators executed during those specific 8 hours. If they had no breakdowns, fast setups, and perfect quality, their net OEE is 95%.
So the operators did their job perfectly.
Flawlessly. But gross OEE measures something else.
What does it measure?
Gross OEE measures performance against the theoretical 247 capacity of the calendar week. There are 168 hours in a week. The machine physically exists for all 168 hours.
Oh.
If the plant only schedules it to run for 40 hours and it sits in the dark for the other 128 hours, your gross OEE is going to be terrible, no matter how perfectly the operators ran it during their shift.
Oh, wow. So net OEE grades the execution on the shop floor, but gross OEE grades the entire business strategy.
Exactly. The massive gap between a 95% net OEE and a 30% gross OEE tells a very specific story. It tells you the operators are doing great, but the sales team isn't bringing in enough orders to justify a second or third shift.
The business is failing to utilize its capital asset.
Right. So if a CEO yells at an operator for a low gross OEE, they are literally yelling at the wrong person. The gap exposes organizational failure, not operational failure.
That is a massive aha moment. You can't blame the machinist because the sales guy lost a major contract.
Exactly.
But let's go back to the floor level problem. Let's assume there's plenty of work. The sales team is crushing it. The plant is scheduled to run 24/7.
Okay, full capacity.
But the net OEE is still garbage. The operator's doing everything right, the machine is perfectly maintained, but the output just isn't there. Why?
This brings us to what is arguably the most frustrating operational failure detailed in these sources.
The tragedy of the multi-department handoff.
Yes, the multi-department handoff is where capacity goes to die. It is a tragedy of organizational silos.
Silos, yeah.
Because a machine doesn't just need one thing to run. It requires a convergence of materials, data, tools, and approvals from entirely different departments, all of whom have different priorities and different bosses.
Walk me through how this actually plays out in real life. How does a handoff fail when everyone thinks they're doing their job?
Let's trace it. You have a scheduled job. The machine finishes its previous work. The operator clears the bed, and the machine is sitting there, green light on, completely available.
Okay, the timer starts.
Now, the production supervisor starts calling around. They call the warehouse to see if the raw material is ready. The warehouse manager looks at their screen and says, yes, the aluminum blocks have been received. They're on a pallet. We are almost ready to bring them over.
Almost ready.
Then the supervisor calls the tooling department. Are the cutting tools ready? Tooling says, yes, we know exactly where the fixture is. We are just about to calibrate it. Almost ready.
Okay.
Then they call engineering. Engineering says, yes, we caught a slight error on the drawing. We are just finishing the revision. Almost ready.
Oh, boy.
Finally, they call quality control. Quality says, yes, we just need the lead inspector to sign the final approval form, and she'll be back from lunch in 5 minutes. Almost ready.
Everyone is almost ready. If you audit any of those departments individually, they get a gold star. They are on top of it.
Individually, they are succeeding. But what does the machine actually have? The machine has absolutely nothing. It cannot cut almost ready aluminum with an almost ready tool. And because everyone was 99% done, The delay doesn't trigger any massive alarms. No single department failed catastrophically. The responsibility just fell into the invisible cracks between the silos.
And when the operator logs this hour of downtime, they use that phrase again, coordination issue.
Because coordination issue is a remarkably polite way of saying that everybody in the building knew a piece of the puzzle, but absolutely nobody owned the final outcome of feeding the machine.
It's so frustrating. The analysis from ManuApp provides a really devastating mathematical example of how this bleeds out across an entire process.
The output funnel.
Yes, the output funnel. They don't just look at one machine, they look at the whole factory through this funnel. And it really illustrates how these tiny handoff failures just destroy a business plan.
The output funnel is a brilliant visualization because it tracks the decay of intention.
Decay of intention. I like that.
Yeah.
Let's track a batch of products through this funnel. Let's say the production planning department looks at the schedule and declares, we are going to manufacture 10,000 units of this product today. That is the plan.
A solid plan.
But because of the minor stoppages we talked about, the sensor jams, the delayed forklifts, the tooling issues, the actual shop floor only manages to physically produce 9,000 units by the end of the shift.
So we are already down 1,000.
Right. Then the quality control department steps in. They inspect those 9,000 units, and they find some scratches, some dimensional errors. They reject 700 of them. So quality only approves 8,300 units.
It just keeps shrinking.
But the bleeding isn't over. Now those 8,300 units have to go to the shipping department. But shipping is backed up. They're waiting on dispatch documentation to be signed by a manager who is in a meeting, and they run out of packing boxes. By the time the truck has to leave the dock, they only manage to physically load 7,800 units.
You started the morning with a plan for 10,000. You shipped 7,800.
Where did the other 2,200 units go?
They didn't vanish in a fire. They evaporated in the handoffs.
It's like planning a dinner party. You invite 10 people, and you buy groceries to feed 10 people.
Okay, I love this analogy.
Right. But you mess up your prep timing in the kitchen, so you only manage to actually cook enough food for 9 people.
Tragic, but it happens.
Then you go to the dining room to set the table, and you realize you only have enough clean plates to serve 8 people.
Oh, no.
And finally, you realize it's raining, and the patio umbrella is broken, so you only have physical seating for 7 people. You didn't fail just once. You didn't have one massive disaster. You failed at every single intersection of the process.
And this introduces the concept that ManuApp focuses heavily on, dispatchable output.
Dispatchable output.
This is the only metric that actually matters to the customer, and frankly, the only metric that pays the bills. A lot of factories celebrate when the machine finishes cutting the 9,000th part. The operator high-fives the supervisor. But that part isn't dispatchable yet.
It's just inventory.
It's just sitting in a bin, waiting for quality, waiting for packing, waiting for a truck.
I want to apply this concept of dispatchable output beyond manufacturing because it is so incredibly relevant to knowledge work.
Oh, absolutely.
Think about a marketing agency. If a copywriter writes 10 articles in a week, they feel highly productive. Their personal output is 10.
They're feeling great.
But if the editor only has time to review 8 of them, and the legal compliance team only has time to approve 6 of them, and the web developer only has time to actually publish 5 of them to the website, the agency's dispatchable output is 5.
The other 5 are just stuck.
The effort that went into those other 5 articles is trapped capacity. It's just inventory sitting on a digital shelf.
If you measure your success by what you start doing, or even what you individually produce, rather than what you can actually deliver to the end user, you are lying to yourself. The capacity is lost in the handoffs.
So, if we are losing all this incredible capacity, literally thousands of units or thousands of dollars in these tiny gaps between departments, the obvious question is, why don't management teams see it happening in real time? Are the executives just completely blind to the floor?
They aren't blind, but they're looking through a severely distorted historical lens.
Historical.
Yeah, they don't see it because of how the data is collected and recorded. This brings us to a major section of the Azuro Digital Report, the severe limitations of manual tracking versus automated tracking.
Let's talk about the traditional setup, because I think people would be shocked by how analog a lot of these multi-million-dollar factories still are. How does OEE typically get calculated in a standard non-digitized plant?
It relies entirely on a human being with a clipboard or a piece of paper.
A literal clipboard.
A literal clipboard. The machine is running, it stops, the operator looks at the clock, they fix the problem, they look at the clock again, they write down on a piece of paper 10.15 to 10.25, waiting on material. They do this all day. At the end of the shift, they hand that piece of paper to a supervisor. The supervisor collects 20 of these papers from different operators and puts the stack on their desk. Sometime on Friday afternoon, an administrative assistant takes that stack of paper and manually types the data into an Excel spreadsheet.
Kidding.
I'm not. And then, next Monday morning, the plant manager opens a dashboard to look at the OEE report.
Next Monday morning, they are looking at a problem that happened last Tuesday.
Exactly. Azure Digital identifies 3 fatal flaws with this manual tracking system. The first, as you just noted, is latency.
Because it's a week old.
The data is entirely historical. Yeah. You cannot intervene in a breakdown that happened 5 days ago. The opportunity to fix the handoff has already passed.
Right. What's the second flaw?
The second flaw is subjectivity. Human beings are inherently biased. If operator A is friends with a forklift driver, they might log a delay as a minor mechanical adjustment to cover for their friend being late with the material.
Oh, office politics.
Exactly. Operator B might call the exact same delay waiting for forklift. The data is polluted by human interpretation and office politics.
So the data is late and it's heavily biased. What is the third flaw?
The third and perhaps most damaging flaw for the performance metric is insufficient granularity.
Granularity meaning like the level of detail.
Yes. Human beings hate paperwork.
It's true.
If a machine stops for 30 seconds because a sensor got blocked by a piece of scrap, the operator just reaches in, clears the scrap, and hits restart. They are never, ever going to walk over to a clipboard, write down the time, write down a code, and document a 30-second stop.
The paperwork literally takes longer than the fix.
Right.
So those micro stops just vanish into thin air.
They completely disappear from the record. But remember the multiplier effect. If that unrecorded 30-second stop happens 40 times a shift, that is 20 minutes of lost production that simply does not exist in the data the plant manager is looking at on Monday morning.
So what does the plant manager think happened?
The plant manager just sees that the machine ran slower than expected, and they assume the operator was just slacking off.
Okay, so manual tracking is fundamentally broken. It's late, biased, and missing all the micro failures. No wonder executives can't fix the readiness problem. They are operating on fiction. So what is the alternative? The sources mention these MES systems, manufacturing execution systems like Cable Maze or ManuApp. How do they actually solve this visibility problem? I want to understand the actual mechanics of how this software talks to a massive piece of heavy machinery.
It requires bridging the gap between physical iron and digital data. An MES system removes the clipboard and removes the human interpretation. It integrates directly with the machinery.
How? Do they just put a camera on it?
Sometimes, yes. They use AI computer vision to watch the machine cycle. But more commonly, they tie directly into the machine's brain, which is called a PLC, a programmable logic controller.
A BLC.
A PLC is a ruggedized industrial computer. When a sensor on the machine detects that a piece of metal is in position, it sends a 24-volt electrical signal to the PLC. The MES system monitors those signals in real time.
So the software actually knows the exact millisecond the machine stops cutting.
Exactly. If the spindle stops spinning, the MES knows instantly. It records the exact cycle time. It records the exact duration of the stoppage down to the second, those 30-second micro stops that the operator never wrote down.
The MES catches them.
The MES captures every single one of them. Furthermore, it forces categorization.
How does it force it?
When the machine stops, the MES can read the error code directly from the PLC error 404, coolant pressure low, or if it's an organizational delay, the system locks the machine.
Locks it.
Yeah. The screen flashes red, and the operator is physically required to tap a specific, standardized reason on a tablet like waiting on engineering drawing before the system will allow the machine to restart. You go from historical, subjective guessing to real-time, objective, undeniable facts.
Okay, I have to push back hard on this. I completely understand the value of the data. But put yourself in the shoes of a machinist who has been working at a plant for 25 years.
Okay, a veteran.
Right. They are a master of their craft. Suddenly, management installs a digital system that tracks their every single movement down to the millisecond. It forces them to tap a tablet every time they pause to stretch or clear a jam.
That sounds awful, yeah.
Doesn't this create a deeply dystopian environment? Aren't we just building a surveillance state on the factory floor? I can see operators absolutely hating this. I can see them rebelling against it or finding ways to cheat the system. How do companies actually get frontline workers to accept this level of micromanagement?
It is a profound change management challenge.
Yeah.
And your skepticism is exactly how the operators feel on day one. They view it as Big Brother.
Of course they do.
But if we connect this to the bigger picture, And if management implements it correctly, the MES actually accomplishes the exact opposite of micromanagement. It becomes the operator's greatest defense mechanism
Wait, how can being tracked to the millisecond possibly defend the operator?
because it stops the blame game.
Oh, I see where you're going.
Think back to the multi-department handoff failure. The machine is sitting idle. In the old manual system, the plant manager walks the floor, sees an idle machine, and their immediate human instinct is to blame the person standing closest to it.
Why aren't you running?
Exactly. They yell at the operator gets defensive, says they're waiting on tooling, the manager doesn't believe them, and morale is destroyed.
Right.
Now replay that with an MES. The machine stops. The operator taps, waiting on tooling. On the massive digital dashboard displayed above the factory floor, the machine's block turns yellow and the timer starts ticking. But the dashboard isn't blaming the operator.
The dashboard is blaming tooling.
The dashboard is flashing a warning to the tooling department. It entirely shifts the spotlight from the person running the machine to the system failing to feed the machine. When the plant manager pulls up the OEE report, the data proves objectively that the operator was available, but the organization failed them. The data acts as an impenetrable shield for the frontline worker. It exposes the systemic silos rather than allowing management to rely on the lazy assumption that the operator's just slacking off.
So it actually clears their name.
Yes. Once operators realize that the system proves it isn't their fault, they usually become its biggest advocates.
Okay, that is a powerful paradigm shift. If the system demands accountability from the engineers and the warehouse just as much as the machinists, it creates fairness.
Exactly.
But let's get incredibly practical here. Let's say you are listening to this deep dive right now. You are an operations director, a plant manager, or a hospital administrator. You completely agree that your readiness is failing, but you live in the real world.
The real world with tight budgets.
Right. You do not have the budget for a massive six-figure digital MES software overhaul right now. Your board will not approve it. The IT department says it will take 2 years to implement. How do you fix this readiness problem tomorrow morning without spending a fortune?
This is where we get to the core operational advice from the field notes. Because you're right, most people don't have the budget to instantly digitize. And the terrifying thing is, when management sees that output is falling behind demand, and they don't have good data to tell them why, their default instinct is usually the most expensive instinct possible.
Oh, I know this one. They decide to just buy another machine. We aren't making enough widgets, so clearly our widget maker is maxed out. Go buy a second one.
Exactly. They try to buy their way out of a logistical problem with capital expenditure. But the field note explains why this is almost always a catastrophic mistake.
Why is it catastrophic? More machines equal more widgets, right?
Not if you have a readiness problem. If your organization is currently suffering from readiness failures, if your warehouse, tooling, and engineering departments cannot get their act together to feed machine A on time buying, machine B does not solve that underlying dysfunction. It literally just creates a second multi-million-dollar place for material not to arrive.
Oh, man, that is brutal. You didn't buy more capacity, you just bought a very expensive parking spot for empty pallets.
You just doubled the amount of waiting time your organization can generate.
That's a huge trap.
You doubled the waiting time, you increased your maintenance overhead, and you halved your return on invested capital. It is a death spiral.
So if buying a new machine is a catastrophic trap and we don't have the budget to buy expensive MES software, what is the low-cost, immediate solution?
It is a behavioral change. It is the strict implementation of what the sources call the next job readiness check.
Next job readiness check. Okay.
And the absolute beauty of this is that you should enforce this on a $20 dry erase whiteboard long before you ever attempt to do it in expensive software.
A $20 whiteboard. I love it.
The fundamental rule of the readiness check is this. Preparation cannot begin when the current job finishes. If you wait until the machine is empty, stops spinning, and the operator looks around and asks what's next, Sand, you have already structurally designed waiting into your process.
Because the clock is already ticking on downtime while they scramble to find the answers, you have to look into the future.
Yes. Before the current job finishes, maybe an hour before, maybe half a shift before, someone, usually a supervisor or a production planner, must physically verify a checklist for the next job. And I emphasize physically verify.
You're just on a screen.
No. This isn't just checking boxes in an ERP computer system.
Yeah.
Because computer systems lie. Inventory systems say you have 10 parts when you actually have 0. It requires walking the floor.
Okay, what exactly is on this $20 whiteboard checklist? Walk me through the interrogation.
It asks very specific, undeniable binary questions.
Okay, hit me.
Question 1. What exact part number runs next?
Seems basic, but good to know.
Right. Question 2. Is the raw material physically staged? And you cannot accept the answer, it's in the warehouse. The answer must be, the pallet is physically sitting in the yellow square next to the machine.
Okay, no vague answers.
Question 3. Are all the required tools, fixture, and inspection gauges physically present on the cart?
Present and accounted for.
Question 4. Is the engineering drawing physically printed and verified as the most current revision?
So no old versions.
Exactly. Question 5. Are all quality and administrative approvals complete?
Okay, all 5 are checked.
But here's question 6, which is the mechanism that actually forces the behavioral change. If any of those previous answers are no, who specifically owns the unresolved item? Who is the named human being responsible for fixing it before the current job ends?
Oh, I love that. You can't just write a vague excuse like waiting on engineering. You have to write, Dave in engineering has until 2:00 p.m. to sign the drawing revision. It strips away the anonymity of the multi-department handoff. It forces public accountability.
And the field note outlines a practical exercise for implementing this. A 1-week trial that any operations leader listening to this can launch next Monday morning.
Tell me about the 1-week trial.
For 1 single week, tell your production team to stop measuring how long machines are idle. The total minutes of downtime do not matter for this 1 week. Instead, force them to record exactly, specifically why the next job couldn't begin immediately when the previous one finished.
So you are auditing the readiness, not the machine.
Exactly. But you have to set strict ground rules for the vocabulary. For this 1 week, you ban the word waiting. You ban the phrase coordination issue. You ban operational delay. You force forensic precision.
So what happens after a week of forcing that precision? What does the data look like?
The patterns that emerge will fundamentally change how you view your entire operation. You stop seeing a vague fog of waiting, and you start diagnosing the real diseases.
Give me some examples.
You will see notes like, material was shown as available in the computer system, but the physical forklift was broken, so it wasn't delivered to the floor.
Wow, okay.
Or, the fixture was available, but it was actively being used by machine C, so machine A had to sit idle.
So they were sharing tools.
Right. Or, the priority of the schedule was changed by the sales team at 9:00 a.m., but nobody informed the warehouse to bring different materials, so the operator staged the wrong job.
Those are massive revelations, and none of those are equipment problems. A brand new $2 million CNC machine won't fix a single one of those issues. They are purely readiness problems.
And this leads to a profound point about capital expenditure and lean thinking. Delaying the purchase of new equipment by simply maximizing the utilization of the assets you already own is the ultimate expression of operational excellence.
Yeah, that makes sense.
If you can reclaim 15% of your capacity just by staging materials properly, fixing your handoffs, and forcing cross-departmental communication, you do not need a new machine.
You just found a whole new machine hidden inside your existing process.
Furthermore, you might even use that newly reclaimed capacity to bring jobs back in-house that you previously had to outsource to expensive third-party vendors because you falsely believed your factory was full.
Oh, because now you have room in the schedule.
You save massive amounts of capital, you reduce your outsourcing costs, you take control of your supply chain, and you drastically improve your profit margins. And you do it all through a $20 whiteboard and a strict checklist.
So, to summarize the financial reality here, the cheapest, most effective machine upgrade you can possibly buy has absolutely nothing to do with the physical hardware of the machine itself. It has everything to do with how you organize the human beings and the workflows around the machine.
It is an organizational upgrade, not a mechanical one. And organizational upgrades, while culturally difficult, are financially free.
Free is a very good price. Let's recap the incredible journey we have been on today because we covered a massive amount of ground.
Really did.
We started by looking at the dangerous illusion of vocabulary. How easily we mistake a machine or a person's availability for actual readiness to produce.
Availability is not readiness.
Right. We decoded the alphabet soup of metrics, learning why reliability and availability are just pieces of the puzzle, and why targeting 100% utilization will actually cause a system to crash into gridlock.
the highway analogy.
We dove into the terrifying, compounding math of OEE overall equipment effectiveness and saw how the six big losses silently bleed capacity.
That math is unforgiving.
It is. We explored the critical difference between net OEE, which grades the operator, and gross OEE, which grades the executives. We mapped out the tragedy of the multi-department handoff where everyone thinks they are almost done, but the machine gets absolutely nothing, leading to a shrinking funnel of dispatchable output.
The dinner party disaster.
The dinner party disaster, exactly. We debated the friction and the immense value of digitizing this tracking with MES systems to shield operators from unfair blame. And finally, we looked at the low-cost, high-impact solution. Why preparation, through a simple whiteboard readiness check, totally trumps the expensive instinct to just go out and purchase more machinery.
It requires a fundamental shift in perspective. You are moving from a reactive posture, running around putting out fires when a machine stops, to a proactive posture, engineering the readiness of the next job before it is ever needed.
Before we wrap up, you usually leave us with something to chew on, something that maybe wasn't explicitly spelled out in the industry reports, but connects all these operational dots to a deeper human truth. What is the final provocative thought for today?
I've been thinking a lot about the psychology behind all of this invisible waste. What if the ultimate bottleneck in any operation isn't the machinery or the supply chain or the lack of software? What if the true bottleneck is human psychology?
Human psychology. Tell me more.
Think about our deep-seated comfort with those euphemisms we discussed, waiting, or coordination issue, or operational delay. Those words aren't just lazy data entry. They act as an emotional shield for the management team.
An emotional shield.
As long as we use polite, passive language to describe our operational failures, we protect our egos. If a delay is just a coordination issue, no single department has to take the blame. We don't have to have difficult conversations with the engineering manager or the warehouse director. We stay comfortable.
And comfort is the enemy of progress.
Exactly. But in exchange for that emotional comfort, we are sacrificing massive amounts of productive capacity and profitability. If you truly want to change your output, you can't just install new software or sign a purchase order for a new machine. You might first have to change your vocabulary.
Wow.
You have to be willing to strip away the polite euphemisms. You have to be willing to look at an empty floor square and say, we failed to prepare, rather than we experienced a delay.
Change your vocabulary to change your output. That is a powerful paradigm shift. And it takes us right back to the image where we started this deep dive. Standing on that immaculate factory floor, looking at the glowing green light on a silent multi-million-dollar machine, staring down at that perfectly painted, entirely empty square labeled Next Job.
It all comes back to that square.
It does. So as you go back to your desk or your factory floor or your software development team today, I invite you to take a hard, honest look at your own workflows and ask yourself, what is the one thing that always seems to arrive last?
That's the question to ask.
Thanks for joining us on this deep dive into the hidden world of operational readiness. We will see you next time.